Okay, so before we get started, I first want to say that I know the course evaluation is available, so I would really appreciate if you can take some time to do this to do the course evaluation for this class. I would really appreciate it. Okay. All right. So I think in today's class, we will continue to talk about some like advanced materials in the time series analysis. So the first topic I want to talk is from chapter 8.5. Okay, so this is cross correlation analysis and pre-whitening. So I think this topic is important, especially for those of you who do this cross correlation studies. All right, so let's start with this very simple example. So we have two time series, xt and yt. And for xt, we assume it is a random walk. And for yt, we assume it is equal to xt minus 3 plus vt. Okay. So here, wt and vt are just white noises. Okay. All right. All right. So you can see that xt and yt has some correlations, right? So yt is determined by xt 3 time periods ahead, and xt is determined by xt minus 1, like 1 period by xt 1 period ahead. Okay, so suppose we have like this 2 time series, and we want to check like what legs we want to use for y. What legs of x we want to use for y. And what we usually do is that we will like pull out those like CCF plots, right? So the cross correlation functions plot and decide like which one has the largest correlation. Then we will pick the largest correlation and do like the following analysis. Okay, so that's our like standard procedure. However, to do that procedure, we usually like rely on we do not like talk much about that, but we mentioned that a little bit at the beginning of this class. So we will rely on some like the asymptotic theories or the large sample series of the cross correlation. Okay, so now let me just help you to record the large sample distribution of cross correlation. So the large sample distribution of the cross correlation is the following. So if xt and yt are independent process, okay, then the large sample distribution, the cross correlation function, which is rho hat xyh. So this is cross correlation function is normal with mean 0 and standard deviation 1 over square root of n. Okay, if at least one of the process is an independent white noise. So a couple of things that we need to pay attention to here in order to use this large sample distribution. So the first is that we want xt and yt to be independent process. Okay. And the second, we want that at least one of the process is an independent white noise. Okay. So as long as these two requirements satisfies, we can use this large sample theories of the cross correlation function. Okay. Or in other words, the confidence intervals you have in your CCF plot is valid. Okay, as long as these two requirements are satisfied. So xt and yt are independent process, and at least one of the process is independent white noise. Then we can have this large sample series. However, like in realities, you can notice that like these two requirements are actually very strong requirements. So for example, back to our example at the beginning, these two requirements actually does not satisfy. Okay, so do not satisfy for our xt and yt. Okay, so it's actually very easy to see. So first, you can see that this xt is a random walk. So definitely it is not an independent white noise. And the second, you can see that this yt is determined by xt minus 3. So it's again, it's not an independent white noise. Okay, and more importantly, both xt and yt are depend on previous value of xt. So that means they are not independent process. Okay, so you can see that the xt and yt, the examples that I just gave, does not satisfy the requirements of the large sample distribution of the cross correlation function. Okay, so how can we do that? So suppose that we still want to study like the cross correlation between xt and yt, or in other words, suppose we still want to know like what xt we want to use for the regression of yt. So how can we do that? Because we know like the large sample distribution of the correlation cross correlation function is not correct. So how can we do that? Okay, so we will try to like we will try to like transform xt and yt so that the large sample distribution requirements satisfy. Okay, so solution. Transform xt and yt so that the two requirements satisfy. So let's call this a first requirement. This is a second requirement. And how can we do the transformation here? So we'll first do a first order difference of xt. So now we have this delta xt equal to wt. Okay, and this is nice actually. This is white noise. I mean this delta xt is white noise. Okay, and since we know that the white noise is independent with all other stuff, so that means this is an independent white noise. Okay, so that means requirement 2, check. Okay. And how about requirement 1? So for requirement 1, we know that we want the xt and yt to be independent. Okay. Okay, and we see that xt or delta xt here is a white noise, so it should be independent with or yt. If we like get rid of like the dependent part of yt. Okay, so what we do is that we will do a same transformation of yt. So let's call it delta yt. This is equal to yt minus 1 is equal to xt minus 3 plus vt minus xt minus 4 plus vt minus 1. Okay, this is equal to xt minus 3 and minus xt minus 4 plus vt minus 1. The first term is wt minus 3, and this is just wvt, delta vt. So now you can see that delta xt and delta yt are independent, which means requirement 1, check. Okay. So now this means if we check CCF of delta xt and delta yt, then we can apply the large sample distribution. Of CCF. So any questions here? So this actually has a name actually for it. So this is called, so what we discussed is called pre-whitening. Okay. So that means is that if we want to study lead lag relations between two time series, we need to make one of it to be an independent white noise. Okay. Otherwise, the large sample properties does not work. Okay. So the example what I gave earlier is just an example of this pre-whitening. Okay, and remember what we do is that because we know xt is a random walk, so we take the first order difference of it. Okay, so that's the delta xt is just a white noise, and we do the same thing on yt, the same transformation on yt, so that's like the delta xt and delta yt will match, and it will also make like both of it to be independent. Okay. Yeah, so the example that we just see is actually a very simple example, but this actually can be generalized to a large picture. Okay, so let's do some steps for pre-whitening. Okay. So let's say that if xt is a Riemann, so if xt follows a Riemann process, then the residues must be white noise, right? Okay. So the idea is that we will first, get the residues. Okay, let me erase this and just write down the steps and explain like the intuitions there. I'm sorry. So let's just write down the steps. So step number 1 is that we will fit an Riemann model to one of the time series. And let's just call this series xt. Okay. So the SI Riemann model is just phi b 1 minus b d xt equal to theta b wt. Okay, so, right, so that's the standard Riemann model. We do the integrated part here by this 1 minus b to the power d, and this is AR part, this is MA part. Okay, so that's the standard S Riemann model. Okay, so we'll fit an Riemann model to one of the time series. Okay, then we will obtain residues WT. Okay, how can we do that? So the easiest way that you can see is that you will move like basically move this like theta b to the left hand side. Okay, so you can write like theta b inverse phi b 1 minus b dxt. Okay, so that's you will get the residues, and in the regression is that you can just call the R to give you the residues. Okay, and let's call this part pi b for simplicity. Okay, so for example, in our example early, so WT is just equal to xt minus 1. So it's just 1 minus b xt. Okay. All right, so that's step number 1. And step number 2 is that we want to match xt and yt so that we will do the same transformation on yt. Okay, so we will use the fitted model to fit yt in the same way. So that is our new yt hat. Now is just pi b yt. Okay, so we use a fitted model, which is pi b. Oops. Okay, so we use the fitted model to fit yt in the same way. All right. So once we do all this step, we know that WT and YT hat should satisfy the 2 requirements of the large sample series of the CCF, right? Because WT now here is just an independent white noise, and YT should also be independent with WT. So it satisfies the 2 requirements of the large sample series. So that means we can then do cross correlation, write it down, cross correlation. All right. Then we can do the cross correlation analysis between WT hat and YT hat, and we can determine which lags we want to use to predict YT hat. All right, so any questions about the pre-whitening or both the logic of the pre-whitening and the steps of the pre-whitening? Okay, so if there's no question, I think I want to just give you an example in R to show this. Okay, so let me switch. So this is an example of the mortality rate and the pollution. So this graph is the CCF function of the raw data of the mortality rate, and I think this is pollution. Okay, so what you can see from this graph here, so you can see clearly there's like those like annual cycle, right? There's like this annual cycle. However, if you just like look at this graph, it's really hard to decide like which lags of the pollution you want to use for mortality rates. It's actually not very clear, right? You can see basically like all these lags are outside this confidence intervals. And you can see all of them are actually like very large. Okay, so it's actually very hard for you to decide which lags you want to use to predict the mortality rates. And what's the problem? One reason of this is that because this mortality rate and this pollution, their correlation function, we cannot use like the large sample series to decide their correlation function because the mortality rate and the pollution are not independent, and at least one of that does not follow a white noise. Okay, so that means if this is a reason, then you would definitely see like this not very good CCF plot. All right, so then what should we do? So how about like we can just like use a pre-whitening, and the first step of the pre-whitening is just to pick one of the time series and do a SRAMA fit to that. Okay, so I think I follow the textbook, and how about we just do the fit a SRAMA model to the mortality rate. So we first plot the data, and you can see that there's a very clear decreasing trend. So we will do the first order transformation on that and plot the ACF and the plot PACF of it. And you can see that the ACF looks like it tails off, and the PACF has a cutoff at lab number 1. Okay, so that means the AR1 model would be good for this deep mortality. Okay, and so that means we can just fit a SRAMA model, and the SRAMA we will use is just like this. The AR part, the AR order is 1, the I order is 1, all other orders are 0. We'll just fit this model to the mortality rate. Okay, and yeah, you can check like the residuals here are pretty good. The ACF of the residuals, the normal QQ plots, the LP statistics, everything looks very good. Okay, so that means the ARAMA 110 looks like a good model to the mortality rate. Okay, all right. So the next step. So let me write down here. So ARAMA 110. So let's fit mortality using ARAMA 110. Okay, so that's step number 1. And from step number 1, we want to get the residuals from this. So the code that you will use is this. It's just like the residuals. And U is our SRAMA fit. So you do U $ fit, then residue. It will give you the residuals. Okay, so we will obtain the residuals from the SRAMA regression. All right, so that's what you do here. All right, so let me run the code, and you can see do the TS plot of the residuals. So definitely the residuals looks good because we already check it's like, oh, it's like it's time series plots, so it looks good. Okay, so that's what we did for step number 1. So that's what we did for the mortality rate. And the second step is that we will use the fitted model to refit the pollution. Okay, so which is the time series Y. Okay, so here is the code that we will use here. All right, so if you check the SRAMA, so you can see that the coefficient of AR1 is negative like 0.5064. Okay, so this command called like the filter, it's a command that we will use to refit the pollution by using the fitted model. So the filter here I use is the AR coefficient from the SRAMA model on the mortality rate. The AR coefficient 1 and 0.5064. Okay, so it's basically negative of this coefficient. Okay, and the size equal to 1 means that we will just use like the previous values to filter it. Okay, that's basically what the AR1 does. Okay, yeah, and also since we do a first order difference on the mortality rate, so here we will also do a first order difference on the pollution. So we have like this deep pollution. Okay, and this is our filter, which is a coefficient of the AR1 model of the mortality rate, and we will use this AR fit. All right. Okay. now we will use this command to, okay, I think I didn't run this. Okay, and I will use this command to create a new data set with transformed mortality rate and pollution. Okay. All right. And having this, let's redraw its CCF plot and see what we can get. Okay. So now this is a new CCF plot. Okay. Let's compare it with the original CCF plot. Okay, you can see it's actually very, very different, right? The original CCF plots, almost all the lags are outside this confidence interval. But here you can see that it looks like only lag number 0, or maybe, I don't know, a couple of lags, like number 4 or lag number 3 are outside like this confidence intervals. Okay, so that's like, I mean, this graph would tell us like what lags of the pollution we want to include to predict mortality. That is lag 0 of the pollution we just want to use the lag 0 of the pollution to predict mortality. Okay, so this CCF plot gives us this, you can very easily read from this graph. However, if you want to see like what lags of the pollution I want to use to predict mortality, the CCF plots basically give you nothing about it, tells you nothing about it. It's really hard to see, but I mean, after you do this pre-whitening, then you can easily got this. And the reason again is because if we do not do the pre-whitening, then the confidence interval, which is this blue lines, this dotted blue lines, actually does not make no sense. But after we do this pre-whitening, this confidence interval makes sense, and we can very easily use this confidence interval to decide which lags we want to use for the to predict the mortality rate. Okay. So that's pre-whitening. That's example. So any questions about it? Okay. So if there's no question, I think I want to talk another topic, which is Bootstrap. So let me switch to the whiteboard. To talk about this second topic, Bootstrap. So Bootstrap. This is SS 8.6. Yeah, so Bootstrap is a very, very powerful method to do the inference. Okay, it's very, very powerful. So when I was a student and when the first time I saw this, I was really like impressed by how powerful this is. So it just looks like magic, but it's actually very, very popular. So I think, and it also has a lot of applications in time series. And so in today's class, I want to give some of its applications in time series. Okay, so Bootstrap help us a lot in inference. So inference, you can just think like finding the standard error of the parameters. Okay, so let me first like give you a quick example of like what is Bootstrap in inference. Okay, so example. Okay. So suppose we have a data set. And this is very simple data set. It's like 1, 2, 3, 4, all the way to 20. Okay. So what's the mean? So the mean is very straightforward. It's just like the mean of this data set is, you can calculate, it's just equal to 10.5. Okay. But the question is that What about the standard error? Or what is the confidence interval of the mean? And basically, just by using this data set, there's no way that we can calculate this. Or I mean, there's no way that we can calculate the confidence interval. Okay, so we can then use the bootstrap to calculate standard error. Okay, so what we do, okay, so I mean, then what is like the bootstrap procedures, or what is a bootstrap algorithms? Okay, so step number one, we draw a sample from the data set. So we just like pick one number from this 1 to 20. So let's say we pick 5. Okay. So now 5 is in our new data set. Okay. Okay. Then we put 5 back and redraw a number or redraw a sample from the data set. Let me write in this 5. Okay. And now let's suppose that the second number we pick is 16. Okay, so now we have 2 numbers in our new data set, 5 and 16. Okay, then we put like 16 back and redraw a sample from the data set again. Okay, so we do this 20 times. Okay, then we construct a new data set. Okay. So let's just have some random numbers. So 5, 16, 17, 20. So we have like a new data set. Okay, this data set is different from the original data set. It's just like we do like all this like sampling with replacement. Okay, so this has a name of it. So this is called like the sampling of replacement. Okay. All right. Then we calculate its mean. We calculate the mean of the new data set. So let's say the mean is equal to, I don't know, is equal to 12. Okay. All right. So we construct new data set, we find its mean. Okay, so that's the step 1 of the bootstrap. The step 2 is to do this algorithm, like say a large number of times. Let's say do 10,000 times. Okay. Step number 2. So we do this, let's say b times. B is a very, very large number. Let's just give it like 10,000 or 100,000 times. Okay, so that means we will construct like 10,000 times new data set, and we will calculate like 10,000 means of each of the data sets. Okay, so we do this b times. Okay, so that means we will b means. All right. So for example, we know that like the example, the first mean is 12. We can maybe say that's the second mean is, I don't know, 13, like all the way to the b mean
let's say 8. Okay, so we'll have B means. Okay, and this is what? So this would give us distribution of the mean. So if you like plot like all this B means in this graph, and you can maybe see that it follows a normal distribution, and it will follow a normal distribution, and the mean gonna be 10.5. Okay. So this is a PDF of the mean. All right. So once you have like this PDF or maybe the CDF of the mean, then that means you can find the standard error of it or the confidence interval of it. Right. So that answers our original question. What is the standard error, or what is the confidence interval of the mean? So if we just only have like one sample, we basically cannot do it. Right? We can only find the mean of that sample, but there's no way for us to find like the standard error or the confidence interval of it. However, we can use the bootstrap to do that. So the bootstrap logic is that we will just use like this sampling with replacement to construct a bunch of new data sets. And for each of the data set, we will calculate a mean. Okay, and we will do it like a lot of times, say like 10,000 times. So that means we will have like 10,000 means. And that would create a distribution of the mean. And actually, you can show that that bootstrapped distribution of the mean is actually equal to the true distribution of the mean, like in large sample, okay? And then that means we can find the standard error and the confidence interval of the mean, okay? So yeah, I have a question here. Multivariate data just as easily. It seems like resampling would be difficult if there are too many variables. That's a good question. So if we have like multivariate data or multiple data, yeah, so we need to do that in a smart way. So this is a simple example. So the example that I give in the time series later would be the example that have like multiple data, because you know that in the time series we are basically running those regressions. So we will basically have like multiple regressions. So you have multivariate data, and yeah, we need to do it in a smart way, which I will discuss later. So that's a great question. Okay, but the point here is that you can see that we can use this bootstrap to find the mean to find the standard error and the confidence interval of the mean. So it's really like magic. And actually, like people show that in large sample, this confidence interval and this standard error is equal to, like converge in distribution or converge in probability to the true standard error and the true confidence interval. Okay, so which is actually very, very powerful. Yeah, so this is what I said, that the first time I saw this, I was really say that this is something like the magic. Okay, so any questions about like the basic ideas of the bootstrap? Okay, so let me show you the R code for this. Okay, so it's gonna have some like loop in that, so which you perhaps haven't seen before. So let me select photos. All right, so this is example.
Okay, so what I do is that this is the example that I just talked about. Okay, so I create a data set 1 to 12, 1 to 20. Okay, all right. Then what I do is that I will do this like replacement, sampling with replacement. Okay, so the code is like this. Okay, so I create a vector called mean, and I first give this mean all NAs. So now this mean is just a vector of all NAs. So you can see here it's just like one NA, but it actually can be like infinite NAs. Okay. All right. Then I say for the first, like for the first vector of this mean is the mean of the first new data set I construct, right? And that first new data set is that I sample from the data set 20 times with replacement equal to true. Okay, so I sample from, let me just run this small code. So I sample from the data where the data is 1 to 20 times. And I will do the replacement with true. So that means if you pick one number, you can put it back and and then redraw it. Okay, so if I run this, and you can say this is a new data set, or this is one of the new data set, it has like these numbers. Okay, and I will do the mean on these numbers. Okay, so I will do the mean, calculate the mean on these numbers. Okay, it's 9.75. Okay, and I will record the first mean, 9.75, to the first place of this mean vector. Okay, and I will do this mean like 10,000 times. So the loop is like this. So for I, basically from 1 to 10,000, you will do all these steps like 10,000 times. Okay, so if I equal to 1, then that means mean 1, which is the first, the first scalar of this mean vector is equal to the mean of is equal to the mean of the first new constructed data set. Okay, and if I is equal to 2, so that means it's the second place of this mean vector is equal to the mean of the second new data set. Okay, and when I is equal to 3, then it's the third mean, it's a mean of the third new data set. Okay, and I will do it like 10,000 times. So once I do this 10,000 times, I will have 10,000 means, and that would create me a distribution of the mean. Okay, so for example, I can plot the density of the mean. So you can see it. Okay, so that's the density of the mean. Okay, so you can see it's pretty much follows a normal distribution, and the mean of this distribution of the mean is approximately equal to 10.5. Okay, so now you can calculate the mean of this mean vector. So it's equal to approximately 10.5. You can find the standard error of it. It's equal to 1.304, and you can find the confidence interval. So suppose we are doing a 95 confidence interval. So it's the 2.5 quantile to 97.5 quantile. Okay, so you can just use this command you can use this like quantile command to find the empirical confidence interval of it. Okay, so that will give you the confidence interval, 7.95, 13.10. Okay. All right, and this would actually be equal to the, if you, this like the lower bound is basically like 10.48 minus 2 times the standard deviation. So it's just like the Z distribution. Okay. But anyway, you can just like use this command to find the empirical confidence interval of the mean. Okay, so this code just did what I just presented. Okay, and in order to get this distribution of the mean, we will use this loop command. Okay, so we'll use this loop. So for I equal to 1 to 10,000, we will do this thing like 10,000 times, and we will take each of its mean and construct a distribution of the mean, and use that distribution to find the mean, to find the standard error, to find the confidence interval. Okay, yeah, and actually people can see that people show that the standard error and the confidence interval would converge to the true standard error and the true confidence interval of the mean. Okay. So any questions? All right, so I think this is a simple example of the bootstrap. And now let's see how bootstrap can help us in time series. Okay, so let me switch back to the whiteboard and discuss it. So bootstrap in time series. So let's just recall for a AR1 model, which is xt equal to phi xt minus 1 plus wt. So if n is large, so if we have like a lot of observations, then the 95% confidence interval for theta, for phi is phi plus minus the estimates of phi z alpha over 2, 1 minus phi square over n. Okay. Yeah, that's what we usually like. What's the R output gives us. Okay, so you always like raise this from your output. All right. This relies on the requirements that n is large. However, if n is small, the large sample distribution do not work. And we can use bootstrap to construct the confidence interval or the standard error of the estimate. Bootstrap. So let me do this example. So this example is actually a very long example. So I think I will first like present the theories and what we do like on the whiteboard, and then I'll move to the R to like show you this example. Okay. All right. So the model we consider is this. Okay. So the model is xt minus equal to mu plus phi xt minus 1 minus mu plus wt. Okay, so this is like some kind of like transformation of the AR1 model, and we pick mu equal to 50 and phi equal to 0.95. Okay, so this is just like a AR1 model, but we just like recenter its mean. Okay, the difference is this. So instead of assuming this WT for assume it follows a Laplace distribution. So the Laplace distribution is like this. Okay, so you can choose, I'm sorry, here's this bracket. But you can choose any like distribution of WT. The point here is that we do not want WT to follow a white noise, okay, or to follow a standard normal distribution. And we will say like this actually like affects the results. Okay, and from this Laplace distribution, one can show that the expectation of WT is 0 and the variance of this T is equal to 2 beta squared. Okay. All right, so that's our data. And now let's work on this model. Okay, so let's call it number one. Okay. So number one is that we will simulate 100 data points. Okay, so we will simulate 100 data points from this model. Okay, we then fit an AR1 to it. Because we know it follows a AR1 model, so we can fit a AR1 model to it, and we will obtain the coefficients. So yeah, this number is a number that you will later see in the R, but since I want to write down like the logic sense, a series here, so I will tell you the number here. So okay, so if you simulate like 100 data points from this time series model, and your WT follows this Laplace distribution, and you fit an AR1 to this 100 data points, you will get like mu equal to 45.25, phi equal to 0.96, and sigma W square equal to 7.88. Okay. And you can see like all these numbers are pretty close to the number in the true data generating process, right? So this is mu is approximately equal to 50, which is our true data generating process. And this phi is equal to 0.96, which is very close to 0.95, which is the true parameter in the data process. Okay. So that's step number one. We just simulate 100 data points. Okay, and you can think this step as like as the example, as last example where I construct the data set that's from 1 to 20. Okay, so in the last example, I have the original data set is a data set from 1 to 20, and here you can see that now I have like 100 data points, and it follows this AR1 distribution, and I estimated. I got the mean. I got the estimates of the mean, the AR parameter, and the residual squares. Okay. All right, so that's step number one. Now step number two. Now let's apply the large sample theory. Okay, so just as I discussed, we know the 95% confidence interval would be what? Would be phi hat plus minus z alpha over 2, 1 minus phi square over n. Okay, and if you plug in the numbers, it's going to be equal to this is your 95% confidence interval for phi, for your AR parameter. Okay, yeah, and let me give you the number. So this is equal to later you will like see like all these numbers from the R code. Okay. All right, so that's the 95% confidence interval if we apply the large sample theory. However, is this the correct 95% confidence interval for the phi? Yeah, for the AR parameter. We really want to ask ourselves this question. Because here you can see a couple of things that might not make this the true or the correct 95% confidence interval. So first, the data set is actually small, right? We only have n equal to 100. This is not a big data set, okay? And number two is that our error follows a Laplace distribution, not a standard normal distribution. Okay, that's maybe the second reason that's causing this 95% confidence interval not reliable. And the third reason is that the third reason that might causing this 95% confidence interval not reliable is that the AR coefficient is like 0.95, which is actually very big. So it's like almost to the stationary, non-stationary boundary, right? The non-stationary boundary is 1, but now here what we pick is 0.95. It's pretty close to that non-stationary boundary, okay, or non-stationary cutoff points. So you can see like all these reasons actually might cause like this large sample theory of the 95% confidence interval not reliable. Okay, so number 3, what is the true confidence interval of our phi? To answer these questions, we can just bootstrap it. Just recall our bootstrap algorithms or the bootstrap logics is that now we have like 100 data points, right? And we will like do this sampling with replacement to construct a like a new data set. And for the new data set, we will calculate a phi. Okay, and we will do it like b times, say like 10,000 times. Then we will have a distribution of the phi, right? And from the distribution of the phi, we can get the confidence interval and the standard error of the phi. Okay. So we generate data from the 100 data points. All right, step number 1. Then for each new data set, we calculate a new phi. Okay. Then we do it 10,000 times to get a distribution of phi. Okay. Then step number 4, using the distribution of the phi, we get the confidence interval. So exactly the same logic that I discussed in the last example, right? So we can use bootstrap to find the true confidence interval of the AR parameter phi. Okay, and in R we find the true confidence interval of phi is actually from 0.7664 to 0.7907. Okay, so you can compare the true confidence interval and the confidence interval from the large sample theories. They are very, very different. And actually the overlap is very small, right? So that means if we apply the large sample series here, we actually, the 95% confidence interval we get is actually not correct or not reliable. Okay. So the large sample confidence interval is not equal to the true confidence interval. Why? Number 1, right now we have a small sample. Number 2, AR parameter closest to the bound, closer to the boundary point. Okay, and number 3 is that our WT now follows
a Laplace distribution. So all these things that make our true confidence interval not equal to the large sample, not equal to the large sample confidence interval. So that means actually the confidence interval you read from your R output is actually not correct. Okay. And the bootstrap tells us the correct confidence interval. Okay. So everybody good with this at this point? Okay. But now here's a problem. I think I might have something wrong here. So let me, yeah, I think yeah, this step is not what I mean here. So we generate the data from the true distribution. That's correct. Okay. So now here's a problem. The problem is that we actually do not know the true model, right? So that is, we do not know phi, which equal to 0.95. We do not know WT follows a Laplace distribution. All we know here is the 100 data points. Right? So we actually do not know like what's the fees, and we actually do not know what's the error term, what's the distribution the error term follows. All we observe is the 100 data points. Okay. So that means we cannot right? That means we cannot find the true confidence interval. Right? So in order the true confidence interval of phi. So all this step do, all this step number 3 do is that it relies on the knowledge that we know what is the true parameter of phi. Okay. So we need to know like the phi equal to 0.95. We need to know that this WT follows a Laplace distribution. Then we can do this bootstrap to find the true confidence interval of phi. Okay, those all relies on the knowledge that we know what is the true phi, what is the true distribution of the error term, and what is like our true model. But the problem is that we actually have no knowledge about it. Okay. So does that mean that at this point we can only use the large sample confidence interval for our phi? The answer is actually no. We can again use the bootstrap to find the confidence interval. And people show that the confidence interval find from the bootstrap is actually equal to the confidence interval, or it is actually equal to the true confidence interval. Okay. So we cannot find the true confidence interval of phi. And more important, yeah, we can use a bootstrap to find a bootstrapped confidence interval of phi, and more importantly, we can show the bootstrapped confidence interval is actually equal to the true confidence interval. Okay. So how can we do the bootstrap here? So let me talk about like how we can do the bootstrap here. Okay. So now just fix ideas that now all we have is 100 data points, and we can fit a AR1 model to that 100 data points. Okay. Write it in steps. So step number 1, we fit an AR1 to 100 data points. Okay, so that means we will get mu hat, we will get phi hat. Okay, then we calculate errors of each observation. So that is WT hat is equal to XT minus mu hat minus phi hat XT minus 1 minus mu hat. And this is from t equal to 2 to 100 because we do not know x0. So that means we can fit, we cannot get W1 basically. Okay. So we get W2 hat, W3 hat, all the way to let's see, 100 hat. Okay, and step number 2. Step number 2 is that we will do the sample with the replacement. So I think that's what back to your question at the beginning. So you ask if the data, so right now you basically have like, we have XT at minus 1, WT, right? So we have like basically three dimension data, and how can we do the replacement here, right? The idea is that we will do the replacement based on WT and use the WT to construct XT. Okay, so we sample with replacement from our W2 hat, W3 hat, and obtain a new data set. Let's call it W2 star, W3 star, W100 star. Okay, right. So we do the bootstrapped based on W, and then we construct XT and XT minus 1 using this W star. Okay, so we then generate a bootstrapped data by the following. So XT star is equal to our estimates. So our estimates is mu hat is equal to 45.25, and our estimate of phi hat is equal to 0.96, XT minus 1 star. This is equal from t to 100. And since we do not have any knowledge about like x1 star, so we'll just pick x1 star equal to the x1 in the original data set. Okay. So now we have a new data set, right? So we have x1 star all the way to x100 star. Right. So we construct a new data set from replacement. I mean, sampling with replacement. Okay. Step number 3 is that we will fix an AR1 to this new data set and obtain, let's see, mu star hat, phi star hat, and sigma w square hat star. Okay. All right. Now step number 3 and step number 4. We will do step number 2 and 3. Let's say b times, and let's pick b equal to 10,000 times. That means we will get a distribution of mu, phi, and sigma w squared. Okay. And step number 5, using the new distribution, we can get the confidence interval of phi. And actually, you can get the confidence interval of mu and the confidence interval of sigma w squared. All right. Okay. And in R, which I will show you later, maybe not today, but Wednesday. So in R, if you do all this step, you can find the 95% confidence interval of phi is 0.78147 to 0.96717. Okay, 78147. So about 0.78, 0.96. If you compare this confidence interval with the true confidence interval, which is 0.76 and 0.96, you can see that they are actually very close, right? What we got, like the bootstrapped one, is 0.78 to 0.97. Okay, so you can see they are pretty close. And more importantly, both of them are very different from the large sample confidence interval, which we know is actually not correct in this like small sample data setting, in this like non-normal error process setting, right? So you can see that the bootstrap actually help us to find the bootstrap confidence interval is actually very, very close, or actually, I mean, in large samples, it's gonna be equal to the true confidence interval of the phi. Okay. So that means we are good. So any questions about like the logic? Yeah, so in next class, I will show you the examples, and I will go over like all these steps and I mean all these logics with you again. Okay, so yeah, please let me know if you have questions on this. Okay, if there's no questions, I think that's it for today's class. Yeah, and also if you have time, I'd really appreciate if you can do the course evaluation. Okay, so thank you very much. I will see you on Wednesday.